2, when we're in school, we're going to hopefully be able to do some of those practicals and look in detail at some other things. But there are some nice, simple things in C2 that we can go through now and get some of C2 covered nicely with offsite learning. So that's the whole of C2: rates of reaction, reversible reactions, crude oil, alkenes and alkanes, hydrocarbons, chemical analysis, Earth's atmosphere and Earth resources. There's some extra bits in there because you're triple. Some of those are a little bit longer. There's much more around hydrocarbons. There's more than alkenes and just alkanes. And in reversible reactions, we have to look at the Haber process as well. But what I'm going to be going through today is rates of reaction, and if I get time, reversible reactions, but rates of reaction more than anything else. Now, this is the last slide. I know it's the second one, but it's also the last slide on these slides. Myself and Mr. Timmins would really like you to try one of these 6 or 4 markers. Okay, now I've kind of arranged them in order of difficulty because at the end, I am going to structure the first 6 marker. I'm going to show you what it needs to have in it. I'm not going to tell you the answer, but I'm going to say it needs to contain these things. So that's a supported answer. If you want to try one that's completely unsupported yourself, the green one is the easiest one to do. Okay, that is a much less complex idea. The yellow one, maybe a little bit more complicated. It requires a little bit more depth of understanding, and it requires 2 different ideas. Red one is very difficult. It's actually quite a complex question to answer. And you have to be able to think of things that I haven't spoken about in this webinar to be able to answer that one. I'm going to suggest that if you're working at level 8 or 9, you should really just go straight for the red one and see if you can do it. If you in chemistry are perhaps finding it more difficult and are scoring sort of 5s or 6s maybe previously in chemistry, then go for the supported one, and everyone else is looking at something in between. Okay, good. Right, so let's have a talk about rates of reaction. So as I go through my slides, I have got down here the things that we're going to look at. So we're going to look at how you calculate the mean rate of a reaction. We're going to look at the different graphs of rates of reaction that you might be presented with and how you look at the rate of reaction at a given time. So the first couple of minutes, I'm just going to show you 2 slides about graphs. I'm not going to get you to draw any, and I'm not going to draw any, but I'm just going to point out 2 really important things. Most of what I'm going to talk about is this collision theory aspect that comes after that you may have touched on before, but I'm going to explain it in much more detail. If we then have time, I'm going to then talk about reversible reactions and Le Chatelier's principle, which is a really important thing in chemistry. This slide has got a link to the freesciencelessons.com videos. So if you don't like my explanation, you think I waffle too much, I'm going to try doing some drawings today to make it a little bit more lesson-like. If you find my drawings hard to follow, freesciencelessons.com, man, his videos are quite good. So before we talk about our rates of reaction, we have to look at the different methods for measuring it. Now, the rate of a reaction means one of 2 things, and they both essentially amount to the same thing. Measuring rate, if up here where I'm moving the cursor, measuring rate is the same as measuring the amount of product made per second or per minute, or the amount of reactant used per minute or per second. So that's the rate, how quickly the products are used up, or how quickly the products are made, or how quickly the reactants are used up. And these are our 3 key methods. This one here, where we've got a clear gas being given off, anything that bubbles and makes a gas, or a metal and acid, marble chips and acid, we put it on a top pound balance there, put a cotton wool bung in it to stop any liquid being spat out, because that would ruin our results. We put it on a top pound balance there, we start a stop clock, and we can look at the change in mass over every 30 seconds, every minute, and then we can plot a graph of that and we can work out our rate of reaction, because the gas has a mass, and as it leaves the liquid, so the mass goes down. This one up here is where we want to actually catch the gas. We want to measure the amount of gas given off, and what we've got here is a delivery tube into an upturned measuring cylinder. We fill this with water, and then as the gas bubbles in, we can see the volume of gas produced every minute, every 30 seconds, every second, whatever it is that we're doing. This one's a little bit more complicated, and you'll get to do this one when we get back to school. If that goes on for a while, I'm going to do it on camera and show you. But this one is when there's a clear color change. So sodium thiosulfate and hydrochloric acid goes cloudy. It goes from being clear to really cloudy, to like milk. And so what you do is you put a dark cross on a piece of paper, you put it on top, and you can time it until the cross disappears. You can change the concentrations and measure it like that. But these are your three methods. This one over here, the one on top of the top hand balance, is the one we use most commonly because it's nice and easy to use in a school laboratory. That's a big hint for you when you're answering those exam questions later. So let's talk about the graphs before we actually get into what reactions are. Now, I've highlighted these three words here because they're really, really important. You're going to get asked two different things. The first is calculate the mean rate after 20 seconds, 30 seconds, 1 minute, but a time. That's the easy calculation, but you're looking for those three words together: mean, rate, after. If that's in the sentence, you're doing this. So it says after 20 seconds. So we go to 20 seconds, we go up, and we go across, and we look at the volume of gas produced. So there it is. It's 36 in 20 seconds. So that's quite easy because we want to know the amount of gas produced per second. So 36 divided by 20, that was 1.8 centimeters cubed per second. That was our rate of reaction. That's how much product was produced per second. That was nice. That's nice and simple. That method you always use when it says mean, rate, after. Okay, you might want to watch this again or have a look at these slides in your Google Classroom just to check that. Now, if it asks for a rate at a given time, doesn't say mean in there anywhere, just says rate, and it says at 20 seconds. That's your clue that it's this technique. Basically, you have to draw a tangent to the curve at that specified time. So a straight line that just touches the curve and has the same amount on either side of the curve. I need to do my hand that way. My mirror, my screen's not mirrored, and it's making it really difficult for me to work out what I'm doing. It's not mirrored for a reason. I'll show you. One of the things that I always do is I try and make the line the same length on either side of where it's touching, and I measure the height of the end of these two things and make sure that they're the same. It's really important that it's got the same gap on either side. And then you work out the gradient of that line. So those are your two techniques. Okay. So rate at a specific time, gradient of the tangent. Mean, you just dividing the amount produced divided by the time taken. Have a look at those two slides. This is not a huge part of this topic. Okay, it's why I've gone over it really quickly, and it's something that we'll practice when we're back in school because it's one of those things that you need to do. Right, 16 minutes in. This is probably the most important idea in chemical reactions, is the collision theory. And what the collision theory says is perhaps actually a little bit obvious. Chemical reactions only happen when the reacting particles actually collide with each other with sufficient energy to react. So particles don't react, no reaction happens unless the particles collide, and they have to collide with enough energy to react. And we've come across that idea before because the minimum amount of energy for them to react is the activation energy. And I'm hoping when you were doing C1, you drew energy level diagrams. Maybe if we just look at what an energy level diagram looks like, just to make sure that you're comfortable with that. So over here, I have got, in fact, let's stop sharing. Let's make it a little bit bigger. So over here, I've got my pens and my paper, just because I thought I might have to do this. And so an energy level diagram is when you had it like that, and we were doing products and activation energy, and it came down over here, and we labeled this as the activation energy there. So we've got an energy level diagram. So this ends up with less energy than it started with, so it's exothermic. Not expected, this isn't meant to be something I'm teaching you now. I'm just seeing if you remember drawing one of those when you did C1. That's an energy level diagram. Okay, so, and it's not the end of the world if you don't remember that from when you did C1. It was just to to help you there with that idea. So they've got to hit each other, and they've got to hit each other with enough energy to make the reaction happen. So that's the collision theory. You have to know that. So it sometimes says, what does the collision theory say? Reactions only happen when particles collide with sufficient energy for a reaction to happen, or with more than the activation energy. You then have to understand how these 5 things directly affect the rate of any reaction. And then we look at how we could measure that. So the first one that they talk about is surface area. Now, I don't necessarily think that surface area is the easiest one to begin with, unless you look at it in a slightly different way. So let's just start off with this. The reason I've started off with this is often in an exam, they will ask you to work out the surface area to ratio of 2 different size cubes, and then which one is going to react faster. The higher the surface area to volume ratio, the more collisions that you get, and so the faster the reaction is. And if you're not comfortable with working that out, have a really good look at that slide there, and then go away and work out the surface area to volume ratio. If you're still unsure about it, again, that's something that you should be asking us about. To give you an explanation as to why that is the case, let's see if my rubbish, I didn't do particularly well at art, drawings actually make that any simpler for you, because let's look at it in a really straightforward way. So if we take that first square up the top, so that's the square like the one that was just drawn in that question, and we've got particles that are reacting with it, and there they are, they're on the outside, so they're hitting the outside of this square, and every time they hit the square, they react with some of the particles in the square, and that reaction goes forwards. If we cut that square up into 4 smaller squares, it's got the same volume, but it now has more surface area. So the surface area to volume ratio becomes larger. And now those other particles can not just hit the outside, but they're able to hit in here as well, because they're in between as well as outside. They can get round to more of the surface. There's more surface to hit. So there's going to be more collisions. And so the reaction happens faster. And that's always going to be the answer when you're asked about why this changes the rate of reaction, because we're always going to be talking about collisions. Why does increasing surface area increase the rate of reaction? Because if you have more surface area, there is more available space for collisions, so there are more collisions, and so the reactions happens faster. It kind of becomes a theme as we go through this. You're going to hear that answer set like that over and over again to try and explain different ideas. So that's surface area. So temperature. Now, this one I think is actually the easiest one to explain. Link the effect of temperature on the rate of reaction using collision theory. Now, hopefully you all have got the idea, if we warm up a reaction, most reactions, they go quicker. Cooking is a great reaction. I really like cooking, and I like chemistry. And if you turn the temperature up, it cooks faster. The reaction happens quicker. Why is that? Well, again, this is about particles. Oh, I'm on the wrong bit. There you go. So if we warm something up, particles start to vibrate. They move more. So if particles are moving more, then they hit each other more often. And when they do, they have more energy. So what happens is we have more collisions, and more of those collisions have got enough energy, so the reaction goes faster. So if someone's in an exam said to you, why does the rate of reaction increase when you increase temperature? The particles move faster, and when they hit each other, they have more energy, so there's more collisions, more of those have activation energy, so the reaction is faster. If we cool it down, they move slower, they don't hit each other as often, they have less energy, the reaction slows down. Either way, we could explain that. That's not too tricky. Just to give you an idea, so when you're drawing graphs and when you're looking at it, if we were talking about room temperature, every 10-degree increase in temperature should double the rate of reaction. So we get that sort of that proportional relationship, okay, until something else becomes a limiting factor, and we'll talk about that later. But when there is excess of all of the reactants, we would get a doubling of the rate of reaction at 10 degrees. Right, now let's talk about concentration and pressure, and we're going to talk about them as the same thing. So again, I'm going to do some dodgy drawings, and hopefully that's going to make it a little bit clearer. And then we will come back, and I'm going to ask you a few questions just to see how we're doing on this before I move on. Forgive me while I just play with my cameras. Oh, that's a good shot to get stopped on there. Fantastic. So there are two boxes that I've drawn. So if we take this as concentration, let's imagine these are 2 glasses of water, and I'm pouring some kind of squash into it. If I poured a small amount into this one, so I just poured a little bit, and there are the squash particles moving around inside the beaker along with water particles that I've not drawn. If I then poured twice as much in, obviously I then have twice as many particles in there. So I had 7, 8, 9, 10. Right. So I had 5 in the first one, so I've got 10. So that is what more concentrated means. There are more particles in the same volume. Okay, we're going to need to be really clear about concentration. It is the amount of a substance in a given volume. So if it's more concentrated, there are more particles in the same space. Now, we all know that if you put more of something in the same space, they bump into each other more often. A little bit like trying to get year 7 into the corridor. They all go at once. They all bump into each other. People go in single file. It works. So because we have more particles in the same space and they're moving, because if we're talking about concentration, we're talking about liquid, because they are moving and there's more of them, they collide more frequently, and therefore more of the collisions have got enough energy, and so the reaction happens faster. We could turn this diagram though into something about gas. This could be a box, that's gas inside. The pressure in here is lower than the pressure in here. This is like a balloon where we've squashed the particles in together. And so pressure in a gas, if we have higher pressure, that means we have more particles in the same space, and therefore they hit each other. Or we can increase pressure by increasing the temperature. But again, if we increase the pressure by increasing the temperature, that means the particles are moving faster, and so they collide more often. So I hopefully here you're seeing a little bit of a theme, that the answer most of the time when we're talking about rate of reaction and the collision theory is they collide more often and therefore the reaction goes forwards faster. So let's have a little look here. So there are more particles in a given volume, so they collide more frequently. That means the reaction happens faster. Particles are more crowded, they're closer together, so they collide more frequently and the reaction happens faster. So that's the collision theory. There is one other thing, and I'm going to have a little look at that in just a second. No, I'm not. Let's talk about that first before I ask. So here's the reaction, the energy level diagram that I talked about, that hopefully you saw back in C1 when you were doing endothermic and exothermic reactions. And here's the energy that all the reactants have got, and down here, here's the energy all the products have got. So this reaction has lost energy, which means it's exothermic. It's given its energy out to the surroundings. But to get it to start, we have to give it activation energy. And a good example of that is striking a match. Got a match, it's got plenty of energy in the reactants there. We know it can give it out because we get light and heat, but to get it to start, you've got to strike it. You've got to give it energy, and that's your activation energy. What a catalyst does is a catalyst lowers activation energy. So here's a diagram. That's what it is without a catalyst. We put a catalyst in and we lower the activation energy. So how does that affect the rate of reaction? Well, if you lower the activation energy, that means more collisions have enough energy. Because if you lower the minimum amount of energy, that means more of them are going to go over that minimum amount of energy, and so the reaction happens faster. Okay. So now we've had a look at those, let's just see if that we can answer a few questions about this. Hang on, let me see if I can get the right one. Fantastic, there we go. So just tell me, let's see who's still awake and who hasn't gone for a cup of tea. I'm sort of halfway through. 4 people still awake. Come on, people. I'll give that 30 seconds. Which of those must be true for a reaction to happen? Give it another 5 seconds. It's still only about half of you. Most of you are getting it right. Come on, wakey, wakey. Yeah, good. That's better. Fantastic. A little bit more interactive now. There's going to be a few of these questions. Okay. Let's end that. 35 seconds in. Share the results. Fantastic. 75% of you got that correct. The particles must collide with sufficient energy. That was absolutely what had to happen. So let's talk about the next bit. 9. Which of these does not increase the number of collisions? One of these things does not increase the frequency of collisions. Which one of those does not increase the frequency of collisions? This is interesting. Although a lot of people are getting it, oh, it's divided. It's very divided. I need to go back over this one in just a second, clearly. About 65% of you have voted. It's quite evenly split between got it right and got it wrong. In fact, I'm going to tell you now about 30% of people have got it right. So that's me. I clearly need to go back over this. So I'm going to stop what I'm doing and go back over this. Let's just end that there. Share results. So 30% of you got the right answer, that it's a catalyst. Catalyst doesn't increase the frequency of collisions. It lowers the activation energy. So let's just flick back over these really quickly. So if we look at these, for the collision theory. So if we increase the surface area, that allows more surface for collisions to happen, so you have more collisions and the reaction goes faster. Temperature, you increase how fast the particles are moving, they hit each other more often and with more energy, so there are more collisions and more collisions above the activation energy. Concentration, we put more particles into the same space, so there are more collisions, and so the reaction goes faster. Pressure, we put more particles in the same space, so there are more collisions and it goes faster. So all of those answers have included there are more collisions or they collide more frequently. The only time that isn't true is with a catalyst. A catalyst does not increase the number of collisions at all. It lowers the activation energy. So more of those collisions have got the activation energy, but there aren't more of them. There are just more of the ones that there were in the first place have got enough energy. There are not more collisions. The activation energy was lowered. All of the others increase the number of collisions. And if you increase the number of collisions, you're going to increase the number that work. Okay, so that is the majority of that one. After this, there are some questions for you to answer, okay, and with some answers on afterwards, okay. So that is the collision theory. That's an absolute fundamental of chemistry too. And that's something that you need to make some flashcards on. You need to know a definition of the collision theory and the 5 things that affect it and what it is that they do. But you also need to have a think back to the very beginning. I'm going to just flick through all of these really quickly and think about how you would measure those differences using one of these things. How could you measure the effect of concentration using this? So we could set this up the same way every time. We could have marble chips that were the same size every time, control factor. We could use 20 centimeters cubed of hydrochloric acid every time, control factor, but we could use different concentrations. We could use 1 molar, 2 molar, 3 molar, and we could see if the rate is different by taking the mass there every 30 seconds, plotting some graphs, and then measuring our rate using the method we had before. We could look at the effect of surface area. We could have marble chips that were big lumps, small lumps, ground to dust, and look at the surface area there, okay? So you need to be thinking about how to tie these things together. That's really important, okay? So you need to learn what the collision theory is and the things that affect it. That's really important. And I know I've gone through it very quickly. If you look at those slides, I think you'll probably accept that it's not the hardest of ideas. And there are some questions there to have a little look. So in the 15 minutes that I've got left, I'm going to see if I can add a bit of stuff about reversible reactions and also perhaps Le Chatelier's principle, because I really quite like Le Chatelier's principle. It's in its basic elements, it's something so simple and it's really important to industrial processes. So any of you that become chemical engineers, this is probably one of the most important things that you will ever learn, because this determines how expensive it is to make quite a lot of things, is whether we can play with this principle or not. So reversible reactions, hopefully you've seen that before. That arrow that goes in both directions means that the thing at the beginning can turn back into the thing at the end, and it can go backwards and forwards. So an example there is, it's not worked on my slides, so let's just move on to another one. You need to know that symbol, reversible reaction. If it's exothermic in one direction, it's endothermic in another. So if a reaction is giving out heat as it goes from left to right, it takes in heat as it goes from right to left. That's always the case. That is always the case. So let's have a little look at an example. I'll come back to that one. So here we go, copper sulfate. This is a simple reversible reaction. This is one that the exam boards say that you have to know. So we have this substance down here, hydrated copper sulfate. You've probably seen that before, because when you did C1, you probably did making crystals as one of the required practicals, and the crystals that you made were these hydrated copper sulfate crystals, and they're very beautiful, they're very blue, they're quite big. And the hydrated copper sulfate, this where it says dot 5H2O, that actually means that the water is trapped inside the structure of the ionic lattice. It's not just wet, it's actually water particles are stuck inside the lattice. So it's actually part of the shape. It's what gives it this wonderful blue color. If you heat hydrated copper sulfate, actually really warm it up, instead of letting it dry in that bowl like you did, you actually heat it on a Bunsen burner, it turns into a white powder, which is anhydrous copper sulfate. So what happens is copper sulfate, pure copper sulfate, is actually just white powder. And so you get steam coming off it. You have to heat it to do that. Now, you can make that go in the opposite direction. If you add water to anhydrous copper sulfate, it gets hot. You can feel the test tube getting hot. And if you just add a couple of drops instead of lots and lots of water, instead of it becoming a solution, it just goes back into being blue crystals. So we can make the color go backwards and forwards. And here's our example of endothermic in one direction. So it's taking in heat. We're having to heat it in this direction, but it's exothermic in that direction because we can feel the heat coming back out. This is a reaction that you have to learn. You have to know that as an example. What they would ask you is what someone would see if they heated it, what they see if they add water. They might ask you to finish off an equation. So this is the most simple one that you have to know. Okay, when I get to the end of this, I am going to take questions. So if you've got questions still, I'll take questions at the end. Now, ammonium chloride. This is one that it would be really good to be able to show you. So perhaps when I'm in school, I'm going to video it. But this is quite a nice one in that it sort of all happens at once. So when you heat ammonium chloride at the bottom, it splits into ammonia and hydrogen chloride, two gases. And as the gases go up the tube, they cool down. And as soon as they cool down, they react together, and ammonium chloride is a solid and it just reappears at the top of the tube. It's not evaporation and condensation. It splits into two separate chemicals that then react back together again to reappear. It's not heating and condensation. It separates and it reacts back again. Now, so that's a reversible reaction. Goes in one direction, can go in the other direction. So ammonium chloride can be heated and split into those two things. Those two things can be added together and they turn into ammonium chloride. We go back this way, you heat this and it splits into two things. You add them back together again, it turns into one thing. That's basically a reversible reaction. But there's a slightly more complicated idea behind all of this. And this is the one that I want to see if I can show you the real reason that I've got a piece of paper. Now, hopefully my drawing is not so awful that this doesn't make complete sense, but I'm going to get you to think for a second now. So this is my reversible reaction. So let me just have A plus B, there we go, becomes C plus D, but also C plus D becomes A plus B. So those two reactions can both happen. A and B can turn into C and D. C and D can turn into A and B. Now, there's a situation where both of those reactions might be happening at once, and that's almost like something out of some sort of comedy sketch. So what I want you to imagine, let me just flick this around so you're not just staring at that the whole time. Let's just imagine this. So those of you who know the school laboratories, let's just imagine D15, because D15 has got a door onto the corridor, but it's also got a door at the back that goes into D12. So you can imagine D15 or D12, any room with 2 doors. Now let's imagine I took 10 of you and I stood you in that room. So we've got 10 people in D15. We're all good so far. There's 10 people in D15. And there's some more of you in the corridor. And what I said was, I want one person to walk out the door at the back of D15. And as soon as they walk out, someone from the corridor comes in through the door at the front. So there's still 10 people in the room. And every time someone comes through the door at the front, someone walks out the door at the back. So you've got to keep watching. Someone in the door, someone out the door. So at any given moment, if you do it simultaneously, at any given moment, there are only ever 10 people in the room. But which 10 people are in the room changes every second. One person in, one person out, one person in, one person out, one person in, one person out. So it's constantly changing, but because you're doing it at exactly the same speed, there's always 10 of you in the room. Always 10 of you. Have a little think about that as a thought experiment. 10 of you in the room, stand near the back door. As soon as someone comes in the front door, one of you go out, and you do it together. So there's always 10 of you, and the person that goes out the back door then goes around to the corridor and lines up ready to keep coming in. And we've just got this same number of people in the corridor and in the classroom all of the time, despite the fact it's changing constantly. Well, that is how this works. So A and B are turning into C and D, but at exactly the same time, C and D are turning back into A and B. If the rates of reaction are the same, it just goes round and round like that. And however much A and B we've got in our beaker, and however much C and D we've got in our beaker, it never changes, because as soon as one of them turns into the other's going back the other way. Really annoying of them. Okay. Well, that idea has got quite an important name. And that idea is what's called a dynamic equilibrium. So let's just see if I can get that back up on here. There we go. Dynamic equilibrium. So in a closed system, what a closed system means is nothing can actually get out. If it's closed, it can't go off somewhere else. Okay, as soon as you take some away, if I grabbed 4 of those people out of the room and sent them to the hall, well, then I've messed up my equilibrium. But while they can't leave the corridor or the room, then I've got a closed system. And if the rate going in one direction is the same as the rate going in the other, the actual amount is not going to change. It will stay in equilibrium. It will stay balanced all of the time. Okay. So that's, I think, probably one of the harder ideas in C2. But if you just think about it a bit, it often is easier to get your head around. I just want to see, is that the one? Let's just, a couple of questions here. Let's just make sure that we're clear about exothermic and endothermic. So answer me one of those. I'm fairly convinced people have gone off to make a cup of tea during that, because it's the amount of people answering is going down and down and down. There's a lot of you here. About half of you have answered. I'm going to give it another 5 seconds. Most of you seem to know the right answer. Ending poll. Right, so energy is taken in from the surroundings. So an endothermic is one that needs heated or takes energy in from the surroundings. So what about if I was to ask you, oh no, I can't ask you that one now because I haven't taught you it. So let's move on. So we've got this idea of Le Chatelier's principle. And Le Chatelier basically was talking about dynamic equilibriums. Let's be really clear. We're talking about reversible reactions that have got an equilibrium. Okay, so my A plus B goes to C plus D and back the other way. And what he said was, whatever you do to an equilibrium, the equilibrium will try and stop that from happening. Whatever you do to an equilibrium by imposing a condition. So if you heat it up, it will try and cool down. If you cool it down, it will try and heat up. It will always try and stop you doing what you're doing. So if you make it hotter, the equilibrium will move to cool it down. So if you've got exothermic in one direction and endothermic in the other direction, the endothermic reaction will speed up in an attempt to cool it down. If you make it colder, and you've got exothermic in one direction a minute, endo in the other, the exothermic reaction will speed up in an attempt to heat up your equilibrium. If you raise the pressure, it will try and reduce the pressure. And if you lower the pressure, it will try and raise it. Now, the question that I get asked all the time when I say that is people say, well, how on earth can the equilibrium change the pressure? So let's just go back to this over here. And let's write something a little bit different. How about if I had A plus B turns into C and back again? Okay. Now I know that looks like a D. That's because I can't write. I'm trying to lean around a camera to do that. Now, if this is contained inside a beaker or inside a container, A and B is 2 particles and C is only 1 particle. The size of the particle doesn't matter. There will be more pressure when we have 2 particles than when we have 1. So if the reaction is trying to reduce the pressure, it will move to this side to reduce the pressure. If we lower the pressure and it wants to increase it, because remember, an equilibrium will always try and stop you doing whatever you've done to it, it moves this way to try and increase the pressure. Okay, so that's how it would do that, because I get asked that all the time. How can it possibly change the pressure? So let's just go back to that. I'm very almost finished now. So, and the same is if we add something. So if we add another chemical, it will move to the side that removes that chemical. If we take a chemical away, it will try and make more of it. Now, I've only got 2 minutes to go. I've not quite got as far as I wanted to. Okay, but that might help. So if we increase the concentration of one, it will shift to the other side to try and reduce it. So there are some things on here that you might want to have a read through, but I am going to go through this again next week. I do not expect you to get all of this now. There's a question there to see if you can work it out. It's mostly the second part of this that I'm interested in. Balancing that is really hard because those numbers are really small. And there's some more questions there about the Chatelier Principle. So if you think you can get that from that, give it a go. But these 6 markers now, this is meant to end in 1 minute, but outlining a plan for investigating how a rate of reaction changes using hydrochloric acid and magnesium. Well, we've all seen that reaction. I know you've all seen that reaction, even if you can't remember. Little strips of magnesium ribbon, putting those into a test tube, you put hydrochloric acid in and it fizzes. So what you need to do is you need to look at how the rate of reaction changes. They're not asking you for it changing with temperature or concentration or pressure. They want you to measure the rate of reaction, the amount of, so you could put in 5 grams of magnesium, you could put in 20 centimeters cubed of hydrochloric acid, and you could take the mass every 10 seconds. And then you could plot the time and the change in mass. And so you've got a nice curve because it will start to slow down because you run out of magnesium. And then you can plot the rate at different points around that curve, taking tangents and working out the gradient. And you can see how the reaction speeds up and then slows down. Okay, so have a think about that one. I've given you a really big clue about how that one works. This one, we're doing a similar kind of thing, but we're going to use different temperatures. Remember, to get temperatures constant in chemistry and biology, we like to use water baths. Catalysts, well, we know that catalysts make reactions go more quickly. Why is that going to be useful in industry? Catalysts are often really quite expensive and so on. So that's me having gone through everything. I've gone over by a minute there. If you're still here and you want to ask a question, please feel free. So the work that you've got this week there are those 4, is it 4? There are those questions on the end of the slides. We'd like you to pick one of those questions and answer it. Some of them are much harder than others. We would then like you to go through the Google quiz, and we would like you to make yourself a revision resource about the collision theory. If you're able to do some stuff on the Chatelier Principle from what I've just told you, that's great. If you're found any of that so confusing that you can't bear it, sign up for a little Zoom meeting tomorrow after you have watched the webinar a second time and read the slides. Okay. So why does the reaction want to stay at an equilibrium? That's really quite complicated, and it's in terms of particles, but the particles will always try and be in a position of equilibrium. And if you make something different, they are always going to try and return to that position. And the reason isn't that it wants to be at equilibrium. If you unbalance the equilibrium, you change the rate of one of the reactions. And by changing the rate, it always moves back towards an equilibrium. An equilibrium is just the state it ends up in. After we do one question in the quiz, do we need to do anything else? Not if you absolutely can remember what Le Chatelier's principle is and you can remember what collision theory is and the 5 things. If not, you need to go back over that. Just make yourself a little revision resource so that you know them. But apart from that, no, you don't need to do anything else. I'm just going to stop the recording